Hi everyone, and welcome to another video. My name is Joel Aviad Ossi, and I am a security researcher at WebSec. In this video, I'll be walking you through one of our recent projects called EduRansW. EduRansW is an educational ransomware or a ransomware simulator, similar to what you might know as a vuln server, but this is more like a vuln ransomware. So it's by design vulnerable so that students or security researchers can actually attempt to break the intentional poor implementations of this code. We will mainly be focusing in this video on how to find the decryption routines using reverse engineering software such as IDA. Feel free to use another one such as Guidra. There's plenty of other decent reversing tools that also are very capable of doing the same job. But don't let that scare you. If you're totally unfamiliar with reverse engineering, don't worry. We'll also be using OpenAI ChatGPT to assist us in the proof of concept code generation. First, allow me to introduce you to EduRansW. I'll keep this short. As soon as we click here on Run Ransomware, it will start the simulation. As you can see, crypt path has been created. This path contains now files with the extension .eduRansW. Once we open this file, oh, sorry, this is because this was open. Once we open this file, it will open this menu. Now, normally, these files, there will be lorem ipsum text, but as we can see, this is now encrypted. The task here is to find the decryption routine in the memory of this process, hook into that somehow, and then make the application think that it's always paid. This way, once we click send money, it will always think that it's decrypted. Keep in mind, this kind of vulnerabilities only work if the decryption key is stored locally. Having said this, let's move on to the reverse engineering part. For this, we're going to use IDA. All right. When you open any software with IDA or any reversing software for that matter, it will often prompt you for a PDB file. And a PDB file is a program database file. Basically, it contains the debugging information and many references to function names and some other things, which is very relevant. The PDB file for the EduRansW software you can find on the GitHub. So if you want to check what the differences are, you can just download it off the GitHub and load it into IDA, and then you'll be able to see the differences. I might be able to quickly show you. Basically, when you load it without the PDB file, it will only show you the functions as sub underscore and then address. Well, if you were to load it with the PDB file, you would have plenty of names here to pick from. So it will make much more sense what each function is doing. It's not a problem. It's just makes things a little bit more complicated. What we have to do now is just search for the errors, and we'll be able to find it in the same way. So we would open this, and we will check, and then we'll see there is confirmations as a text string, there is amount received, and amount is not yet 10 BTC. So what we would like to do is search, for instance, for confirmations. And as we can see, some text references have been found. Let's pick this one. And now we gotta wait for IDA to finish analyzing the binary. And once this is finished, it will open up the IDA view, which personally I find much more reliable. This might take a little while. I'll probably pause the video right now and then resume it as soon as it's done. All right, it's done. So now we are in the IDA view, and it looks like this. And this is how it looks like. So we can clearly see this is the error, where the error happens. And this is where the successful decryption happens. So we want to go a layer up. We want to see what's happening here. Where does it all begin? So everything begins here. And usually whether it goes to an error or a success happens in the end. So this one or this one will have something to do with the error. We can also see here push error amount. This is probably what's triggering this. Maybe if we patch JZ to JMP, maybe this will bypass this. What we are more curious about is what's actually the condition here. For example, this. Let's see. This is where we're going to use OpenAI, because I don't expect everyone to understand this. So let's ask OpenAI, see what it has to say. I'm only going to take this last part. Or you know what? What's might be even a better idea is it will just take this slightly this way. So it's still in res. We probably want to search for this in the functions. So that once we make a picture, GPT might be able to use this. It shows the start address, which is where everything begins. It will be useful for OpenAI. And we make a picture of this, and then we'll move over to OpenAI. Now I'm just going to pause the video and type some text, and then we'll resume in a bit. Actually, before we move over to this prompt, there was one more prompt I wanted to show you, and that's just to copy this and to ask it what is happening here. What any return condition. Well, let's just make it what is happening here. Let's see what it says. And sure enough, it gives us a whole bunch of information, some of which don't really, it's not really important to us. But as we scroll down, this is actually very useful information. Like we can see here what these routines are doing. So we can see here that the call to the routine on 403 E70 likely is a routine that parses or validates the retrieved Bitcoin address. This could indicate that there is some checks there going on, such as confirmation checks or some other payment checks, which is actually what we want to bypass, right? But then we can also see here the move ESI EAX captures the return value from this, like a success or a failure. So yeah, if we can make this always success, then we can always trigger the decryption process. Checks whether succeeds ESI is 0. So we always want to make this ESI return 1. So basically it holds the value true or false, whether it's failed or succeeded. So now with this information, we can actually prompt GPT to make us the hook. Now, I'll type the prompt and then I'll resume the video in a bit. So just before I submit the prompt, I just want to explain a few things. I'm basically prompting OpenAI to use Frida in Python, and I'm prompting to with the information that it has. Oh, now that I'm thinking about it, it probably doesn't have enough information. Maybe it does, because it just needs to know the start address, and then using the start address with this, it will probably be able to calculate the RVA. I'll just post a screenshot here, and I'll give it some information it can work with. There you go. And since we figured out that sub 403 E70 likely holds the validation, and which we can also check this. We can like click through, and we can see here that this is probably where the double spending security happens, where it checks the address, I guess. Let's see. Transactions, probably. This is probably something to do with transaction. Confirmations, yeah, see? So this is probably what we are looking for. Going back to the relative virtual address, relative virtual address is a memory address which is always being calculated like a static address. Um, maybe most of you probably have used cheat engine before, right? If you open a process and you restart the game, um, you'd notice that the addresses are no longer there. You will need to actually find this. It's because the addresses that are loaded by default are absolute addresses. They change because of ASLR, which is a security for memory address randomization in Windows. So it's important for us to find the static address, one that always points to the correct one. And actually, GPT can assist with that. So we give him the prompt to find this right address specifically for this routine. And we prompted that it should always return one no matter what, and automatically hook to the process by process name. Otherwise, it will generate you a code which takes an argument or takes a process ID. It all works, but arguably you'd want the Python script to immediately work the moment that you run it. So this is why we choose this approach. All right. So it generated some code, but I couldn't see the RVA here. So I suppose that it didn't do this correctly. So I prompted another message like, where is the relative virtual address to this routine? And then it calculated it. And this should be it. So let's give it a try. Hopefully this works. So now let's open this and run. And let's see. Nope. So I need to figure out why. Oh wait, maybe it was. Hold on. Yeah, I had to restart this. Let's try again. It was still running in the different code, not this one. And there you go. Now let's see if this really worked. Yeah, yeah, and there we go. This is it. This is it. All right. So yeah, basically, this is how you do. This is how you do this. And there are some other ways you can. In essence, you can probably also try and locate where the decryption key is stored, and eventually make decryptors based on the key, because many ransomware store a local key or even store the key in the memory of the variant itself. So they don't store it in a file. They don't necessarily store it in a registry. Sometimes they do, and you can find that by literally reversing it. You can also sometimes they even store it just in their code itself. You can There are some ransomware variants that are made in C#. You can literally just read the IL code, open it with what was the name, like DN Spy, I'm not sure, or IL Spy, something like that. And you'll be able to like figure it out. Like if it's not obfuscated, if it's not secured, um, or crypted, you'll be able to figure out a lot. Another way to get past this, you can probably also tamper with time. Sometimes ransomwares use NTP servers to fetch the time from. You can spoof that in order to extend the time. Um, the Bitcoin address that are being generated, sometimes you are even able to modify it in the memory. So you can probably just change the address to your own. And if that's not properly validated, you can basically make the application think, even if the key is service on the service side. Um, Although I'm not sure about that, that becomes usually complicated. But in some cases where it's really not properly coded, you might be able to change the Bitcoin address to your own and then pay to yourself in order to make the application think that you've actually made the payment. Yeah, or you can just modify the amount to something like incredibly low and then try it out. But you never really want to pay to you never want to pay to the bad guys. Please don't. This is also one of the reasons that I've decided to make such a video. I couldn't really find um, any well documented decryption processes or tutorials out there. So I might be making more if this is interesting. One final thing on a closure note: if you want to try this out by yourself, feel free to go to GitHub, to our repos, and you'll be able to find the uh, EduRansW educational ransomware here. And you can find a lot more about this over here. You can download the code and try it out yourself. Or if you just want the binary file, you can also download it from the website, from downloads, and then you can download it from over here. I hope this was an educational video. Thank you for your time. Thank you for watching, and until next time.